So hello everyone, and welcome to the class. We will talk about about recursive definitions, about recursively defined objects, functions on these objects, and then structural induction to prove properties about these recursively defined objects. And I hope this will be complicated enough that it will take your mind off tomorrow's election. Okay. Yes, this is the best. If you are nervous about election, the best method I recommend for you is to read about recursive definitions and see how they work. Read more examples and try to prove stuff over these recursive definitions. This will take your mind beautifully off any problems you have, not just political, but in general, any problem you have in your life. I recommend recursion as the answer. I mean, really, it's beautiful stuff actually that we are doing here. Okay, so let's just jump to it. Let me see if correctly positioned. Okay, and our speakers view. Okay, seems to be in focus. Okay, good. So look, we had a certain blueprint for recursively defined wrong color, recursive definitions. Hold on. Oh no, not good. Go back a little bit. Recursive definitions of sets and more generally, or oh well, it's just a different name really. Data structures. First, some base case objects are inserted into the set that you're defining, and that's the base case of the definition. And the recursive step is that if some objects, x1, x2, ... maybe several of them, are in the set, then so is some construct, some function, construction function that takes these objects as arguments and constructs a new object is in the set as well. And this is some procedure. Otherwise, in other words, function. Okay, so examples we have seen, bit strings. We have defined using this. How did we do that? Well, we said in a base case, empty string is in the set of bit strings. I call them BS. Sorry for that acronym. Lambda, the empty string, is in the set, and also if any x is in the set, then x0 and x1 are also in the set. Okay, and this was string x concatenated with a bit 0, string x concatenated with bit 1. This is an example where this is construction really one. So this is one construction applied to string x, which what does it do with string x? It outputs x0. So that's an example of a construction function that takes some elements and constructs a new one, very simply by concatenating a 0 to it. Here, is an example of another construction function. And what that one does is output this. Okay, so I guess this is not the most general because we can have many of these construction functions. Okay, so here is straight away an example where you have two construction functions, and there can be many construction functions, not just one. Okay, what else did we see? Fully properly nested parenthesis strings, right? We said this open close is in the set, and also if any two strings are properly nested parenthesis strings, then so is a string formed like this, open, and then whatever the string is, and then finalized with a close. And also, simply concatenation of these two strings is still a properly nested parenthesis string. Okay, so another example. All right, let's do examples. Actually, in here, in both cases, the construct, so this is a construct that took A and outputted off. Well, it's so horrid. It's, you know, here the parentheses are, you know, I better not write this because it basically on the right hand side is the same as on the left hand side. But here, this designated a function input, and this designates not a function input, but concatenation of a bracket character string and a bracket character. But these are, again, examples of some constructions where finally we have more variables than two. So this is the case of x1, x2 being in a set, and some construction using x1, x2, which simply concatenated. x1 is here and x2 is here, right? So this is the blueprint, and this is the particular instantiation, right? I don't have to use these variable names. Okay, how about this? Integers, oh, you know what? No, positive powers of 2. Okay, so I want my set S to contain all powers of 2, or you know what? Skip positive. Okay, powers of 2. So I wanted to have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, etc. In other words, what integers are those? It's 1, 2, 4, 8, etc. Okay. Here is the quick recursive definition of the set. First of all, I want 1 to be in the set S. So these powers of 2, the set will be called S. And what's the recursive rule? Well, how about this one? If X is in the set, then 2 times X is in the set. Let's see if this recursive definition successfully defines the set. Okay, how do you check? How do you use? You should think of a recursive definition as a code. I mean, okay, of course you can think of this in many ways, but one productive way for some purposes, namely checking precisely what this recursive definition generates, is what it defines, is think of this as a code. In a base case, some elements are explicitly inputted in the set, and this is a little code that says if that the moment something is in the set, then some procedure involving that argument is the output of it is going to be in the set as well. So let's see what this loop generates, right? What was our procedure for determining, you know, how does a recursively defined set look like? Well, number of recursive rule applications, okay, and here is set S. So the base case is that we don't use this rule at all. We just look, first of all, what is being input into set by a base case. So we don't use the recursive rule. Therefore, we use this thing. Okay, set S contains just this base element 1. Okay, how about using the recursive rule once? Well, if X is in the set, then so is 2X. How can I possibly instantiate this clause? Well, there's only one way to instantiate. The only element in set S is 1. So X has to be bound to 1. And if X is bound to 1, then 2X is 2. So I now, basically my set is, looks like this. Okay, now what about 2 applications of the recursive rule? All right, so let's apply the recursive rule again. If X is in the set, X now can be either 1 or 2. Using X equal 1 is not productive, because if X is equal 1, then 2X is 2. So we already entered this into the set. Basically, instantiating X with 1 is not going to create any new elements. So what's the other option? Well, okay, how about X equal to 2? Therefore, this thing will be equal to 4, right? So after 2 applications, my set looks like this. After 3 applications, you can check, instantiating with 1 or 2 doesn't give me anything new. So the only way I can enter something new is if I instantiate X equal 4, in which case 2X 8. So that's how my set looks. And well, you can convince yourself that this little code is going to generate all powers of 2. Okay. And actually, you can prove this by induction. N applications of the rule is going to create 2 to the n. And if that is so, then one more application is going to create 2 times bigger element, and 2 times bigger than 2 to the n is 2 to the n plus 1. End of the proof, right? If you're trying to prove a following statement, n applications of this recursion creates 2 to the n. That is something that I just sketched the proof by induction of, okay? And that will prove that indeed this recursive definition defines all powers of the set of powers of 2. Okay. Questions on this? Okay, maybe we do another example. Okay, how about positive integers? Okay, how can we have this blueprint of recursive definitions. We enter some elements as a base case, and then we have some recursive rule for how to create a new object given some existing objects. Okay, so how about this one? Let's add 1 to the set. And actually, you have many choices for the recursive rule, but let's do this. If X is in the set, then X plus 1 is in the set. Okay, and it's exactly the same way as we did, as we did here. Without the number of recursive rules applications and what's in the set. And if I take just base case, my set looks like this. If I run this rule once, the only way to instantiate is within 1, and 1 plus 1 is 2. So my set is going to look like this. If I run this rule again, the only new thing is going to be created when X is equal to 2. So my set is 1, 2, 3, because 2 plus 1 is this guy, right? and so on and so forth. You can easily prove by induction that the following predicate, n applications of the recursive rule, is going to create a set of positive integers all the way from 1 to n plus 1, right? So each positive integer is created eventually by this, and therefore, in infinitum, this generates all positive integers. But it's not necessary. So this does successfully generate all positive integers, but it's not set in stone. Many other recursive definitions would define positive integers as well. So here is positive integers, alternative code, right? Alternative recursive definition. Well, let's start with the same base case. That seems hard to avoid. But how about, for example, this? If x, y is in the set, two objects are in the set, then so is x plus y. Okay, so this will generate nothing else. It will generate all positive integers as well, right? You can see that you cannot, the following predicate is easily proven by induction. You cannot generate, this cannot generate anything but positive integers, right? Because if you ran it n times and it was true that what you generated is some set of positive integers, then one more application of this instantiates these with some elements, but that's what your inductive assumption that everybody is in here, put in here so far, is a positive integer. So these two must be positive integers, and a sum of positive integers is a positive integer. So the inductive step is done. If n applications created only positive integers, then so must n plus 1, and therefore any number of applications will generate positive integers only. Okay, so now that you established this cannot generate anything but some positive integers, are you sure that it will generate all of them? And yes, you are, because you can always consistently instantiate y as 1. So if you convince yourself that this code generates all positive integers, then so must this one, because it's a more general case, right? So in particular, y could be always 1, and therefore this rule could always resolve into this rule. Okay, and you already know that this rule generated all positive integers. So different code, the same outcome, but I guess in some sense this code is faster, right? Because you can generate, let's say, 8 faster, because 8 can be a result of adding 4 plus 4. And so now you have to just create 4. How could you create 4? The fastest way would be by adding 2, by instantiating this 2 and both of them being 2. And in order to generate 2, well, all I have to do is to instantiate, right, by 1. So you see, this just used 1, 2, 3 steps of 3 applications of recursive rule, while here I would have to use recursive rule 7 times to get to 8. Okay, so the code might not be as efficient, but it's equivalent, as in it generates the same set. Okay, By the way, what would this generate? One is in set S, and two, if xy is in S, then so is x minus y. Let's see what it generates, okay? So one is in the set. So let's the only way to instantiate x and y is with one. So the first rule is going to create 0. Yes, there's no other way. Okay, the next time, maybe, well, x can be, they can be both 1, in which case they generate 0. They can be both 0, in which case they just regenerate 0. But what if x is 1 and y is 0? Okay, that's not interesting. It generates 1 again. Well, how about x0 and y1? Actually, that is the only productive way. So this will generate, I mean, the next interesting thing, okay, so how about this? 0 applications, I mean, the number of applications and set S. If I don't do anything, I only have a 1. If I run 1 once, now my set is 0, 1. And the only new thing you can create running the recursive rule again is -1. Okay, how about now? I have many choices here. X, Y, X can be -1. Clearly, if Y is the same as X, I just generate 0. So that's not interesting. So how about X -1? If Y is 0, that's not interesting either. But if Y is 1, well, I generate -2. And I already have these guys. Can I generate something new on the right side? Yes, by taking x1 and y -1. So if x is 1 and y is -1, then x minus 1, y is 2. So I will generate 2. And basically, you can see now that if you do it 4 times, well, actually, what do you get? So actually, it's not just -3. So -3 is with x is 2 and y is 1, or many other choices will generate -3 I wanted. So let's say x is -2, y is 1. So -2 minus 1 is -3. But x is -2 and y is 2, I already generated -4. So actually, this thing will look like that. Okay, and so how can I generate 3 and 4? X is 1, x is 2, and y is -1. Then I generated 3. X is 2, y is -2. I generated 4. You can see how this behaves otherwise, but basically, what is the conclusion? Integers. And clearly, you have many other ways to define integers, right? Integers alternative. Well, I can do tons of stuff. I mean, how about this? 0 in S, 1 in S, and then if xy in S, then x plus y in S, and x minus y in S. This would be a much more natural way, right? I start with some points that are at least, a little apart, and I add them. So this part clearly generates all positive integers already because it subsumes this part, right? So anything that was
Professor, just to let you know, you're cutting up a bit.
Say this again. The audio is bad. well, I would just repeat what I said. So by the fact that this part is exactly what's here, right? You know that this definition generates all positive integers. Oh, I'm so sorry. It looks like I was just completely kicked out. Do you guys hear me now?
Yes.
Yes.
Sorry, well, I just lost connection. Okay. So the fact that this part copies this means that this thing will for sure generate all positive integers. And if you just look at the subset here, you can convince yourself that negative integers will be generated as well. I mean, just because if all positive integers belong to the set and 0 belongs to the set, then in order to generate any negative integer, say minus n, all you need to do is to instantiate x with a 0 and y with n. And so because every positive integer is in the set, therefore n is in the set. And that means that minus n is in the set. Right? So I would, this is a more natural definition. But this smaller code that doesn't explicitly put anything else into the base case, but a single element, and actually doesn't have addition in its construction rules, turns out to generate the same class, the same set of all integers, both positive and negative. It's a more concise code. It's harder to see. You have to run it to see that it indeed does. Okay, you can again prove it because you can state it as a hypothesis about the number of applications of this rule and make a hypothesis, what kind of integers does this number create? And given that hypothesis, you will be able to prove that the next invocation of the recursive rule will extend this set in some very predictable way. Okay, but I will leave it to you to make that type of hypothesis about this code. Let's see some other examples. Unless you have questions to these. Okay. So something more complicated still. So far we saw how to basically generate different classes of bit strings, parentheses and bit strings. In the book, you can see other examples of classes of bit strings. For example, bit strings that are they start the same way they end. So they're symmetric. But let's generate a new class of objects. Let's show a recursive definition of binary trees. Okay. Now, binary trees, there's many subclasses of binary trees, but let's give one. Binary trees are sort of graphs with an extra structure and some constraints. So they are drawn vertically with some vertex on top. That vertex is called the root of the tree. And the word binary means that every vertex has at most two branches going down. These are called children. And they end with some other vertices. So let's say C and E. this thing is called the left child of A, and E is called the right child of A. And then we recurse. So C might have two children, let's say D and H, okay? And E might have two children, let's say I and Z, okay? And so on and so forth. However, so let's say, well, there is nothing stops us from reusing these vertices. So what are these vertices? Any constants. So these could be integers, could be bits, they could be strings. There could be any other objects. These are basically data structures. You define what class your vertices live. Are they integers? Are they bits? Are they bit strings? Or what have you? And you store that class of that type at every vertex. So, but here's an example where this guy H has only one tree, one. So, okay, M, okay, and perhaps this guy has no leaves, no children, but this guy does, and no, and perhaps N has some sub. You know what? Let me use unique variables so you don't. You have G. Okay, G. Okay, this is still a binary tree. It's not. It's not a full binary tree because, for example, this guy has only one child, and this guy has, and yeah, it's not full because this guy doesn't have one child. It's also not balanced because this guy has one child who's, this subtree has depth 1 and this subtree has depth 3. Okay, but these are all binary trees. Now, I will use the following convention that when I construct a binary tree, if I say that that A's children are an empty string and some other objects, then I'm going to basically represent this visually in this way. It's as if there is no left child. So, okay, and likewise, if I give A two children, both of them are empty, then I will just treat it as if he doesn't have children at all. And of course, symmetrically, if I build a tree like this, I will just visually interpret it this way. So this guy has no right child. Okay, how would we? So this is what what I would like to. I would like to define this type of data structures. They're super useful to organize data in. Like, for example, you will see later, you can do binary search very easily if this is a sorted list. It allows quick search over a data structure, because if there is some predicate that these things are ordered, you check whether the predicate is satisfied on the top, and by ordering, if what you're looking for is smaller than A, you go left, and what you're looking for is higher than A, you go right. You can quickly get to every position, in every element in your data, because if there is n elements in your data, the depth can be at most log n if it is packed correctly. Okay, so this is not example, but if you packed these elements a little better, then this would be the case. So it's not as simple, because if you build this data structure, you have to be able to inject and delete elements, and keeping a tree balanced and assuring this is not so easy. So you will learn this in data structure classes, but that's the main point of binary trees in computer science. Okay, so let's define these objects recursively. Okay, so here is my definition. The base case it will be, okay, I would just declare an empty string to be a binary tree. Okay, and a recursive rule is, I'll make it like this. If T0 and T1 are two binary trees, then for any vertex A, so A here is a variable. It can be E, C, D, H. So here, these variables are constants. I mean, sorry, these variables. These letters represent constants. Here, it is a variable. Then for any vertex A, the following thing is a binary tree. I take A and I give T0 as a left child to A, and I give T1 as a right child to A, and this object will be a binary tree. Now you can ask, what on earth are all these signs? You know, the brackets, the putting together. Well, they correspond to the following procedure in a data structure. These are, let T0 and T1 be some data structures that look like this. And this is, for example, T0, T1 is yet another tree, perhaps smaller than this, perhaps larger, perhaps balanced, perhaps not balanced. There's some binary tree. And then I take T0 and T1 and build a new tree. T0 is a tree here that has some vertex, it has some root, and it goes in some way, who knows how. Yes, it has certain depth, whatever, but that's its vertex. T1 is also a tree that has some vertex and continues somehow. I make here two edges and I put A here, and this is my new tree T. Okay, so this is a construct. It's a construction using variable A and two trees. So if you compare it to this blueprint that we had, okay, right, the blueprint was you insert some elements into your data structure. Well, an empty tree is a binary tree. That's the one. And then you have some construct, recursive construct, which says, if some elements are in your data structure, these are my two elements, then so is some output of a function that takes these elements and constructs a new one. That's the function. It takes two trees and creates a new one using an additional input that defines what this vertex is. Okay, this little guy was not present here, right? Well, you can think of this in the same way. Look, when we defined binary strings, 0 or 1 were not part of here, of the syntax. There were some sort of other constants. That's the same role that this vertex A is playing here. Okay, let's look. So this is our our recursive definition. Let's do what we always did, which is check what kind of objects this constructs. Okay. Okay. So, in other words, let's look at the number of recursive rule application, and trees and BT elements. So in other words, elements of the set of binary trees that I apparently constructed using this this recursive code. Let's see how this recursive code operates. So the simple case, no recursive rules at all, where the only binary tree is the one defined so by the base case. Okay. How about a single application of a rule? Well, what does it do? T0 and T1 must be in the set. Well, the only thing in the set is an empty tree. It's an empty string. So both T0 and T1, the first time you run this rule, have to be instantiated as a lambda. And vertex A is some vertex, like any of these A, C, E, I, G, any of these variables here. Okay, so what it takes this vertex and basically adds empty strings. But I said that by convention, I'm going to represent this in a simpler way, as a tree that simply has no children, as a vertex that has no children at all. So adding an empty child, empty string as a child, is as if you're not adding any children. Okay, so this is because in these data structures, I have to be able to end somehow. So I can pretend that this thing looks like this, and this looks like this, but you can see that this is just useless, annoying thing to draw data structures in this way, right? I will have to laboriously add lambda lambda to the bottom of every node that end. The nodes at the bottom of the binary tree are, by the way, called leaves. Okay, so some terminology, this is a root, and all these guys here are leaves. A leaf is an element of the tree that has no children, right? And you can see that these are the guys with no children. Okay, so that's only the single vertex. And of course, A is arbitrary. Could be any other constant. To be perfectly formal, it's better to say what is the class of vertices this definition goes over. So I can declare binary trees whose vertices are bits. If I do that, then it's really exactly like bit strings that I created. There are only two cases for A0, A equal to 0, and A equal to 1, because that's the only possible two bits. And if I want to create, trees whose vertices are bytes, then in some sense I have 256 rules of this type for A equal to 256 possible bytes. Okay, but of course I'm not going to write these 256 rules. I'm just going to write one saying for any vertex in this implicit universe. Okay, so let's see. That's the only tree I can create using this recursive rule just once. How about I use it once more? What can I do? Okay, so now I have two binary trees, empty one and a single vertex. So how do I instantiate? Okay, I take some vertex. Well, I'm going to call that vertex B, okay, because I just don't want to have another A in the picture. And let's consider 4 cases, T0. So if T0, T1 in BT, T0 could be empty or A. T1 could be empty or a single vertex. Sorry, this really, you shouldn't read it A. You should just think of this, any tree that contains only a single vertex. So if it's a tree of bytes, this can be any byte. Okay, so if T1 is empty and T2 is empty, then all I read is again this, but that's not interesting. That's a single vertex again. Okay, so that's not an interesting case. What about T1 is empty and T2 is a single vertex. So I will this will create a tree that looks like this, which by my convention can be represented simply in this way. And symmetrically, if T0 is a single vertex and T1 is an empty string, then I will also generate this type of tree. And finally, if both T1 and T2 are single vertices, well, then I will call, let T0 be a single vertex called A, and let T2 be a single vertex called C. So this is my T0, this is my T1. They both look like single vertices. Okay. So again, in this picture, so this single vertex tree is already in here, but these are all new type of trees, right? A node with a single with just a right child, a node with a left child, and a node with two children. You can see that this now will generate, 3 rules will generate all trees of depth 3. Because I take a variable and I make T0, T1 be any empty single vertex, vertex with the right child, vertex with the left child, or a balanced vertex with two children. And if I do any combination, then I will generate, so let's consider T0 empty, but T1 ranging over these things. Well, I can create this thing again, but it's already, that type of stuff is already in the set. So that's not an interesting one. What about if T1 equals like this? Well, I will generate this type of tree. It's a tree, it doesn't look very much like it. It's a tree with an empty left, A has an empty left child, and but a non-empty right child, whose name is B. And that B has again an empty left child and a non-empty right child, whose name is C. Right? If I use this tree as my as my T1, then this type of tree will be added. And finally, if I use this tree as T1, then this type of thing is going to be added. Okay, and so all of these are cases of T0 being an empty string, but T1, being in the set, being ranging from all possibilities of trees that we already have in the set, right? But these are just the cases for T0 being an empty string. And if T0 is non-empty, then you will generate everything, all the trees of this type, right? And also, if say T0 now is a singleton, so you will generate everything like this, and so on and so forth. You see, you will basically generate all trees with depth smaller or equal to 2. Okay. What is the depth of the tree? You may ask. You should. So the depth of the tree is the length of the longest path you can follow. So starting from the root. So if you start from the root, it takes you 1, 2, 3 to reach this guy, 3 to reach this guy, 3 to reach this, but 4 to reach this one, 4 to reach this one, 3 to reach this one, 2 to reach this one. This is the depth this tree has depth 4. Okay, and people define depth differently. So somebody can treat a single vertex as depth 1 or as depth 0. Here I will, assume here that single vertex has depth 0. This is going to vary from one person to another, and I forget what the book does at this point, whether it declares a single vertex as the depth 0 or as the depth 1. You have to go relative to the definition that whoever wants. It's a convention. Either one is fine. Okay, so that's the kind of class okay. So we are running out of time. I think this is all that we can do today, but hopefully now you're convinced that this very small code, which is contained right here, that it actually generates all binary trees. Okay, and it's again the power of recursive code, that it's really concise and basically captures all data structures of this sort. It generates all of them. So next time we'll define functions over recursively defined objects, and we'll use structural induction to prove properties of recursively defined objects. And now questions.
Professor?
Yeah.
Could you go back to the table for the recursive rules definitions for the binary tree?
Mm-hmm.
Okay, so in row recursive rule application 2, you can have the tree with 2 children, A and C, correct? A being T0 and C being T1. Will you have a binary tree that is B with the left child being C and the right child being A?
Yeah.
Or does it only...
So no, but you see, these names are this stands for any variables. I mean, any elements in the implicit universe. So let's say that the vertices are bytes. Okay, so this stands for really any single byte. It's not just character A. It's not the single, say, ASCII character who encodes lower capital A. This stands for any element of the implicit universe, like for example, a byte.
All right, so it's completely implicit.
Basically, it means what I meant here is this is any tree whose vertex is a byte and who has a non-empty left child, some byte, and a non-empty right child, some byte.
All right, yeah, that makes sense.
Okay.
Right,
yeah, it's kind of hard to render it as because people can ask, are these things constants? Are these things variables? How to tell when you have this type of code that here A is a variable and it goes over some implicit universe. But if I give you a fully formal one, then it's really hard to parse also. So it's some compromise between full formalism and yeah.
All right, thank you.
Yes, you're welcome.
Hello, Professor.
Yes.
How are you doing?
Hello, ask your question.
Yeah, so I wanted to ask if there is a difference between depth of a tree and a height of a tree.
Oh, you know what? I forget what it is. Maybe there is, but right now I don't remember what it was. So maybe there is some conventional difference. I just forgot about. I don't remember.
All right, then it'll probably be in the book then.
Yeah, I would use them interchangeably, and I cannot think like why not. But if I see, yeah, I think they are interchangeable. I think these are interchangeable notions.
Sorry, I didn't mean. I googled it, and sometimes they're interchangeable, but sometimes they're used for slightly different. Where the depth is like the height of sort of the most filled, and whereas the height is the longest possible path, like the depth of the longest possible path, or something like that.
The only variability in here, so I think height and depth, everybody thinks of them as interchangeable notions, and the only variability in these things is whether you declare a single vertex to be of height or depth 0, or you define it as a height or depth 1. But everything is up to a this constant, right? So either way you go, it's just you increment everything by 1 or you decrement by 1. So it's basically like whatever is more convenient in a context.
Thank you.
Hey, you're welcome.
They
it's something similar to like, whether the first element of an index is of a sequence is the 0th element or it's a 1 first element, right? And it is endlessly annoying that sometimes it makes sense to index your array as starting from 1 and going up, and sometimes it's more convenient to index your array as starting from index 0. And unfortunately, you're gonna have a bug if you forget that somebody indexes from 1, you think they index from 0, you're off by 1. We all wish that wouldn't be the case, that everybody indexes their arrays from one of them, either 0 or 1, and no variability. But that is just not the case, right? Some people are going to index from 1, other people will index from 0. The same as sequences. Some people will write them as the first element is a 0th index, and some people will write them as the first element is a 1. And you cannot do much about it except like get used to that. Sorry, I blocked somebody who tried to ask a question.
I also have a quick question.
Yeah.
So if you go to like when you applied the recursive rules to the binary tree, can you say that that the like number of recursive applications is equal to the depth of the tree? So basically, any tree for the last one, it would be any tree. Oh, okay, you already wrote that down.
So if the depth of a single vertex is 1, then the depth of this is 2, and the depth of these trees is 3. And right now I'm pretty sure that that's how the book defines it.
Okay.
Especially if you declare an empty string to be a tree, then this guy has a depth 0, and this guy gets a depth 1, etc. Yes. So yeah, I mean, you're going to get that if you change this by 1, declare your single vertex as having depth 1.
Yeah, thank you. Your note answers it there to the side. I just didn't see it.
Oh, okay.
Thank you.
You're welcome. Any other questions? see that there's tons of questions on a chat, and I hope maybe these so if somebody has like an outstanding question, they would just post it on a Piazza to clarify. I see most seem to be answered. Okay, I'll stop recording.